Question 21. To do this kind of question, you're looking for optical isomerism. So looking for a chiral carbon. So carbon asterisk usually is what they ask you to write or draw out on your diagram. So draw out and see for yourself. I would always suggest students to draw skeletal formula because that is the fastest. And I got that one wrong. So they want, what do they want? They want 1, 2, 3. So they want 2 chloropropane. So 3 carbon, straight chain, propane. And I've got a chlorine at position 2. 1 and 3 are the same, CH3 and CH3. Carbon from 4 bond, you only show 1 bond, there is 3 hydrogen. Carbon from 4 bond, you only show 1 bond, there's 3 hydrogen. Carbon from 4 bond, 1, 2, 3. You haven't shown 1 more, there's 1 hydrogen there. But the left and the right are the same, so A cannot be chiral there. Okay, no chiral carbon. 1, 2 dichloropropane. So you got a 1. So now I have 1, 2, 3 like that. 1, 2 dichloro. So now I have a chiral carbon because this central one, the left and the right hand side are no longer the same. This side has chlorine, this side has no chlorine. There is 1 hydrogen and there is a chlorine there. So B is already my answer. If I were in an exam, I would have moved on because I already got my answer. I know how to draw from the name. Okay, 1, 3 dichloropropane is gonna look like this. 1, 2, 3. Again, there's a symmetry about the central carbon there. This is a CH2 and CH2 cannot be chiral. This is also a CH2 cannot be chiral as well. C must be wrong. If you have D, you have 2, 2 dichloropropane. Well, this is definitely wrong because this central carbon has got 2 chlorine there. So you don't have 4 atoms that are the same. In fact, 2 chlorine are the same, 2 CH3 are the same. You don't have chiral carbon there. Question 22. So methanoic acid has acidic properties, but it can also has this characteristic of an aldehyde if you see the structure by drawing it out. So that is where it looks like carboxylic acid, but then you can see the left hand side, this bit here, it looks like aldehyde, CHO. The fact that it looks like aldehyde, it can react with phthalings, it can react with toluenes, it can also be oxidized further, okay, by using acidified KMnO4 for instance, where it will go purple to colorless. So here, what will give the same observations with phthalings reagent? So they already told the information there that it could behave just like aldehyde. So if we look at phthalings, so we know that we have that, and then we have CH3. COOH. So that is option A. Option A. Actually, I don't want to draw a table because they all have the different thing, right? So this one will react with phthalings, and phthalings reactant consists of this blue solution. The blue solution is a result of a copper 2 plus aqueous, but of course it's mixed with something else. And then when in the presence of aldehyde, if aldehyde is present, what you will get is you will get a reduction of this phthalings reagent, and you will form this copper plus 1. It's called copper 1 oxide. Copper plus 1, you need 2 of them to balance the charge of O2 minus. This is a brick red precipitate, a result of this oxidizing agent getting reduced, and therefore this one will get oxidized. So this methanoic acid will get oxidized by phthalings reagent. But you want same observations, so you're looking for something else that will be oxidized by phthalings reagent as well. If we look at A, we have a carboxylic acid. Carboxylic acid not oxidized further, so that means no reaction there. You won't get the same reaction. B there is an ester. Draw and see for yourself. This is a methyl. Hang on. This is a methyl because 1 carbon alcohol, and ethanoate. So this is methyl ethanoate, 2 carbon there. Okay, so ester doesn't give you the positive result with phthalings. You can't oxidize ester any further. For C, you have a ketone. So follow the structural formula: CH3, CH2, CO, CH3. Carbon from 4 bond. That's the key rule with skeletal formula. Ketone is not oxidized any further. When you have D, D is aldehyde. So CH3, CH2, CHO, you can oxidize this bit further to give you a carboxylic acid, and therefore, this will give you a positive result with phthalings reagent. Having said that, both of them will give you positive results. Both of them will give you brick red precipitate with phthalings reagent. So this is the answer that we are looking for. In this next question, we have compound Q, which we can make from propanone. Propanone is a 3-carbon ketone. So what we have here is 1, 2, 3, 4, 5, and 6 carbons. What type of reaction will, well, actually it's got nothing to do with propanone, so propanone can make this, but what type of reaction can this product undergo? So we can very clearly see that this is a ketone, as next to the carbonyl we have carbon and carbon, and then we also have an alkene here. So this is about the reaction of an alkene as well as reaction of a ketone. An alkene will typically undergo an electrophilic addition mechanism, whereas a ketone will typically undergo a nucleophilic addition mechanism as part of the case studies associated with these two particular functional groups respectively. So we're going to have both nucleophilic addition at the carbonyl and electrophilic addition at the alkene carbon there. Is that correct? Yep, okay. Because the nucleophilic substitution is typically for halogenyl alkanes, and it's not just only nucleophilic addition because this alkene here is very rich in electrons, so it's the attacking species, it attacks electrophile, whereas a result of the CO there is your carbon delta plus and your oxygen delta minus. This is being attacked. This carbon is attacked by nucleophile. Question 24. Depletion of ozone layer. So which one will cause the most depletion of ozone layer? In terms of these, we're looking at the chlorine radical being a main culprit. So between the energy of a CF, which is stronger than the energy of a CCl, as this one is a shorter covalent bond. And if you have the data booklet, you can have a look at the bond energy. The shorter covalent bond will result in the stronger covalent bond for the CF. So it's actually the CCl that will break, and they will break homolytically in the presence of UV light in the upper atmosphere, and they will give you chlorine radical, and that chlorine radical is the main culprit in the depletion of ozone layer there. Question 25, we have this compound X. So we have two of these CCl bonds. You can hydrolyze it, so it can be broken down or can be broken up by hot NaOH aqueous, because that is your source of your hydroxide as your nucleophile, and they can attack the CCl, delta minus, delta plus, the delta minus Cl, delta plus carbon. So we could undergo a nucleophilic substitution mechanism. These COC bonds cannot be hydrolyzed. So the COC cannot be hydrolyzed. Which one is the COC? So this one is the COC, which I've highlighted in green, the COC, and this one is COC as well. Okay, so all of those COC, they are not hydrolyzed at all. So at the beginning, before hydrolysis, how many of them are secondary alcohol? Secondary alcohol, the carbon with the OH, bonds to two other carbon. So primary alcohol, the carbon with the OH is bonded to one other carbon. Tertiary alcohol, the carbon with the OH is bonded to three other carbon. Let's have a look at before hydrolysis. This is before hydrolysis. So what do we get here? This thing here, this is the OH. The carbon with the OH is bonded to one and two other carbons. This is a secondary alcohol. If I just write secondary as secondary like that, this one here is also a secondary alcohol. The carbon with the OH is bonded to one and two other carbons, so secondary. This carbon with the OH is only bonded to one other carbon. This is a primary alcohol. This thing here, this is a secondary alcohol, and this is a secondary alcohol as well. And I think that's all the alcohols. So there is 1, 2, 3, and 4 secondary alcohol, and not 0 secondary alcohol, obviously. So A and B are out. After hydrolysis, what we're going to get is the Cl. This will be replaced by OH. So we will have an OH there instead. So what I'm going to do is I'm going to cancel out the dipole. I'm going to draw an OH there. So this carbon there, the black color one, is I'm going to highlight that. So this black color carbon bonded to the OH is going to be bonded to 1, 2, and 3 other carbons. So this thing here is a tertiary alcohol. This is new. This is a new one after hydrolysis. And you also have another OH there, courtesy of the CCl being hydrolyzed. And now you have this carbon with the OH, the one highlighted in black on the far left. The carbon with the OH is bonded to 1 and 2 other carbons. and because there's another hydrogen there, this is a secondary alcohol. So this one is new and this one is new. So after hydrolysis, you still have your primary alcohol. You still have one more primary alcohol. So by right, you will have to work out the tertiary and the secondary like that. But you can see there's one tertiary alcohol. I've added an additional secondary alcohol, 1, 2, 3, 4, 5. So there are 5 secondary alcohol after hydrolysis. C is the only correct answer there. Question 26, we have this compound here. Each compound is warmed up with acidified potassium dichromate 6. This is the oxidation number of the chromium. Chromium plus 6, but you have this species called dichromate 6. It's actually Cr2O7 2 minus, or the formula is K2Cr2O7 for the full ionic compound there. You need the acid in order for the acidified potassium dichromate to work as an oxidizing agent. This is your orange color. It will go to green as it forms these Cr3 plus aqueous. It get reduced from chromium plus 6 to chromium plus 3 because it oxidizes the alcohol in each of these cases, except for D, because in D cannot be the answer. Hang on. No. D is not really the answer we're looking for, but I think D is the answer here, because I was just saying that D cannot be oxidized because this carbon with the OH, the carbon with the OH is bonded to 1, 2, and 3 other carbons. There is no hydrogen there to be lost. If you cannot lose any hydrogen, you cannot be oxidized. Tertiary alcohol, because the carbon bonded to the OH is bonded to 1, 2, and 3 other carbons, tertiary alcohol is not oxidized any further. The alkene is not oxidized by potassium dichromate 6. You need a hot concentrated acidified KMnO4 to oxidize the alkene there. So the fact that you get there, so it remains orange because the oxidizing agent just simply doesn't have an alcohol that can oxidize. Whereas if I look at this is if I look at each of these highlighted black colored carbons, the carbon with the OH here for part C, for option C, carbon with the OH is bonded to one other carbon. Primary alcohol can be oxidized. Therefore, this will be orange to green coloration. The same goes for the other A and B, because this is a primary alcohol. Carbon with the OH is bonded to one other carbon. Carbon with the OH is bonded to one other carbon. This is also a primary alcohol. So all of that will be orange to green. I probably don't have to write that because I can just copy that. That's the beauty of working on the screen here. I get to just copy stuff, but you know, in a real exam, you're probably thinking about the color change in your head. Chromium plus 6 in this Cr2O7 2 minus, going to chromium plus 3, chromium 3 plus, green in color. You will see these color changes here, but you will not see any color change here where it remain orange. This is going to be the one that gives you a different observation to the other three there. Question 27. What's the mechanism for this ethanol reacting with HCN in the presence of a base? The base there really is your Na plus Cn minus as your catalyst. So this is your catalyst. The condition for this reaction, as a result of this being quite volatile, low boiling point, you need to keep these reactants, as a reactant. So you don't want to reflux it. So typically you do this to 15-20 degrees Celsius, essentially cold enough temperature to prevent this from vaporizing away. What is most important is you have this Cn minus. It uses the lone pair on the carbon to act as a nucleophile. So option A, this first bit is correct. The nucleophile attacks the delta plus carbons and then break this carbon oxygen double bond. This one is okay as well. What is wrong with the C? C is definitely wrong because that doesn't do that, like that. And D is simply initiation, propagation. This is talking about free radical substitution, which is not the case for these reactions where the mechanism is very clearly a nucleophilic addition as part of your carbonyl chemistry in AS. So A, B, and A and B. Okay, so we look at the next one. Here, you are losing a H minus, which is not likely. You don't lose a H minus. Instead, what you get with the oxy anion intermediate. So you will get a double hump energy profile diagram as you proceed via an intermediate. Uses a lone pair there to protonate because your actual reactant is HCN. It's polar, but it's not ionic like this. That's why we need a catalyst to kickstart the reaction. And having done that, it protonate, give you back the lone pair to the carbon. You kick out the Cn minus. You regenerate back the Cn minus. even though it's not the exact CN- from the catalyst that you started out, but you get the exact same chemical species coming out. Therefore, a catalyst is not used up, it is regenerated at a reaction, and that can be used to, continue the reaction until the reaction is complete and use up all the HCN. You will always kick out one CN- to regenerate back the catalyst in this reaction. So B must be the correct answer there. 28, you have menthol and menthont. Which statement about this compound is correct? So we have a ketone there, as next to the carbonyl on either side you have carbon and carbon, and this is an alcohol. The carbon with the OH is bonded to 1 and 2 other carbon. This is a secondary alcohol. Now, which statement is correct? Both compounds can undergo mild oxidation. Ketone can't be oxidized any further because there is no hydrogen on that carbonyl carbon. If you don't have any hydrogen on that carbonyl carbon, you can't lose what you don't have to begin with, cannot be oxidized any further. But secondary alcohol can be oxidized to ketone, obviously, so not both compounds. That is wrong. Both compounds will give you an orange precipitate with 2,4-dinitrophenylhydrazine. 2,4-DNPH will give you an orange PPT with a ketone or aldehyde. But you only have a ketone here, so you don't have aldehyde here, but the ketone will give you orange PPT. But this is a secondary alcohol, it will not give you any precipitate at all with 2,4-DNPH, therefore not both compound again. Option C, menthol can be formed from menthont, so from menthont to menthol, that one is going to be reduction. That's the opposite of oxidation. To do reduction going from here to here, I can use a reducing agent, whether I use LiAlH4 or I use NaBH4, both of which can reduce ketones. However, this NaBH4 cannot reduce carboxylic acid. To reduce carboxylic acid, you need a stronger reducing agent. That is your lithium aluminum hydride there. So C must be our answer. Why D is wrong? D says it gives you a positive test when you warm it with tolerance reagent. Well, because tolerance reagents is the test for aldehyde, whereas ketones cannot be oxidized any further. So, you don't get the silver precipitate or silver mirror. Tolerance reagent is your silver +1 oxidation number in your silver diamine with 2 ammonia. That is your silver +1 oxidation number, giving you silver precipitate as it gets reduced, okay, because it oxidizes something else, which is typically the aldehyde. But you have a ketone that cannot be oxidized further, therefore no change at all. D will not be a positive test, it will be a negative test. Question 29. What is the skeletal formula? 2-methyl pentane 1-ol. The first thing you do is 5 carbon straight chain, 5 carbon longest chain. It has a OH at carbon 1. So 1, 2, 3, 4, 5. It has a branch. The branch is at carbon 2. This is 2-methyl. This is pentane 1-ol. Very clearly, A is already our answer. How about the rest of the options? So 4 carbon is my longest chain for B. This is butane. This is butane 1-ol. And then I have 3-methyl butane 1-ol because CH3 methyl is at position 3, butane 1-ol, 4 carbon longest chain. This is 1, but nope, I will get a longer carbon if I do 1, 2, 3, 4, 5. So that is indeed pentane, but this is pentane 2-ol without any branches whatsoever. For D, I get 5 carbons and I get 4-methyl. The branch is at position 4. And then this is pentane 1-ol. So it is pentane 1-ol, but the branch is at position 4 instead of at position 2. A is the only possible answer there. Question 30, we have aspartame. It's used as an artificial sweetener. So what do we need? If you warm it in aqueous alkali means you are in basic conditions. Which one of the bonds 1 and 2 will be broken? Broken there? Hydrolysis, hydrolyze, because what we have there is, this is an amide linkage. If you think about it, it's the amide bond. And then this one is an ester bond. You learn ester and amide from your IGCSE, GCSE or O-level last topic in organic chemistry as part of polymerization. This is formed between a carboxylic acid and an alcohol. This is formed between a carboxylic acid and an amine. So both of them can be hydrolyzed in under basic conditions. So both of them will be broken. Both of them will be hydrolyzed. either under acidic or under basic condition. In this section B type of questions, so we have these 4 options that actually represent the various combination of the statements, or the selected options just being whatever that they want us to do. So this section B has been scrapped out from the current A-level syllabus. However, just because they have scrapped out a whole section B does not mean that they cannot ask you questions that are of this type. There could be more than 10 questions. There could be lesser than 10 questions. It is within their right to ask you any questions now because they no longer specify there is a section B. Okay. In this first question, the relative molecular mass of a sample of chlorine is 72.0. As you know, the definition of relative molecular mass is to do with the average mass of blah 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 relative to 1/12 the mass of an atom carbon-12. So which properties of the atoms in this sample will be the same for all of the atoms? What do we know? This is about isotope, isn't it? Chlorine 35, chlorine 37. They are the 2 different possible isotopes. So how do you get 72? You get 72 when you have, well, when you have 35 and 35. So you could have 70. You could have 35 chlorine and 37 chlorine, which is the same as 37 chlorine and 35 chlorine. Both of these will give you 72. So we have 70 there, we have 72. And last but not least, chlorine 37 will give you 74 as your molecular mass. So what is happening is, if we want the one which is 72, that means we must have one of 35 and one of 37. So this question is really asking you, what is the same between chlorine 35 versus chlorine 37? That is what this question is asking you, okay? In terms of what is different, it's just a different number of neutrons. Neutrons are uncharged. Because your neutrons are uncharged, they don't affect your attraction between your valence electrons and your nucleus, because they don't contribute to the nuclear charge at all. Therefore, they don't attract or they don't repel more. They just occupy the space in the nucleus. Therefore, they don't affect radius whatsoever. They do have different nucleon number because you have different number of neutrons for the isotope. And as such, the isotopic mass is going to be different as well. So only one is correct. That's option D there. Question 32, this is about the size of the ionization energy of an atom. It's about the magnitude. So going from an atom, so X gaseous atom. So when you lose 1 mole of an electrons from 1 mole of gaseous atom, you form 1 mole of a gaseous ion with a +1 charge. So this is the full equation, full balance equation with the correct stat symbol. Which one will influence the size of ionization energy? The charge on the nucleus is definitely influenced by the number of protons, and therefore they will contribute to what we call the nuclear charge. So that is an important factor to explain ionization energy. That's usually the first factor I talk about. The amount of shielding is also very important, because as you have, when you lose the shells, so when you have to go to the inner shell, they'll become much more difficult to remove because they'll be closer to the nucleus, less shielded, etc., etc. The distance between the outer electrons and the nucleus, of course, this is a factor as well, because the further out you are, the more shielded you are from the nucleus, and therefore you'll be much harder or much more difficult to remove. Therefore, 1, 2, and 3 must be correct there. Question 33, we're looking at ideal gases. So we know that there's a certain factor here, so something new, which is to do with this thing called density. And there is something new as well as there called concentration. So we know density is mass over volume, as you know from physics and also basic science, I guess. Concentration in this case will be the mass over volume. So let's try and think about PV equal to nRT. This is our ideal gas equation. So what do we know here? PV equal to mass over mR times RT. They have decided to replace mR with just m, so I'm just gonna do big M there. What else? Density is mass over volume, so I could potentially try to find number 2 first, because we always work statement number 2. PV is there. I'm gonna see if I can get the concentration, which is concentration is mass over volume. So that doesn't quite make sense, because when I look at that, you think about P is equal to M over V times RT over M. m over v, mass over volume, is concentration times RT over m. And this thing is not PV, it is simply pressure on its own without the PV, and therefore this thing is PV and it's got concentration on the right hand side. Number 2 is wrong. Definitely only number 1 is correct there. Okay, I can start by showing PV equal to mass over mR times RT. So density is mass over volume, so P is equal to mass over volume times RT over M. So P equal to rho, which is density, RT time divided by M. So 1 is definitely correct. Okay, so big M there is supposed to be at the bottom, so there is supposed to be mass RT divided by the big M and not like that. So 3 is definitely wrong as well.